All right, this is your lesson on limits at infinity, chapter 3.5. Yes, we're going to talk a little bit about limits again. So let's get started here. We're going to determine the limits at infinity for finite functions. And we're also going to determine the horizontal asymptotes, if there are any, of a function. And we're going to determine the infinite limits at infinity. So now we have finite and infinite. So finite just means that there is going to be some set value, and also infinite limits, which is going to go to infinity. I know this sounds kind of funny here. We're talking about x here, and this is y. So we're going to determine the infinite limit, the y value, or the f of x, going to infinity for a value of x going to infinity. And basically we're going to talk about the end behaviors of a function. What does it look like on the ends of the graph? Okay. Let's think about this function here. And if we make a table of values, it is going to look like this. 0, and we're going to let both ends, we're going to take larger and larger values of x and smaller values of x going to infinity. If we let x go smaller without any end, we see that the function, or the y value, is going to get closer and closer to 3. We plug these numbers in here. And if we let x get larger and larger, we also see that the y value, or the f of x, goes to 3. Okay, just to show you what the graph looks like. In the graph, as x gets larger and larger in the horizontal direction, that's the x value, the vertical direction, it gets closer and closer to 3. Okay, in both directions. Alright, so this is just a quick thing here in words, what they're trying to describe as the limit for x going to negative infinity, f of x goes to 3. And as x goes to positive infinity, f of x goes to 3. And this is just saying that the limit as x goes to negative infinity of f of x is equal to L. L is my limit. That would be the 3. Okay, that's what the L stands for. Or if the limit of x goes to positive infinity, the function goes to a limit. Means that the limit does exist, and the limit is equal to L. So just a recap here of the definition of a horizontal asymptote. If we have a limit as x goes to infinity on both ends, or even on one end, we're going to have a horizontal asymptote. See, this is a boundary. And a horizontal asymptote, or an asymptote, is a line where the graph gets closer and closer to, but never can touch. Okay, and remember that the equation of an horizontal asymptote is actually an equation, so you have to use the y is equal to, the y tells you it's horizontal and it's equal to some value, which in this case is 3. Y is equal to 3. It's the horizontal asymptote because the limit as x goes to negative infinity reaches a certain number, that number here. And these numbers could actually be two different numbers, and you'll have two different asymptotes. Okay, this is a theorem that they keep referring back to. I don't use this too much, but it just says that if you have some constant value and you let x go to infinity, and x is the base, and r is some positive rational number like 1 or a half or 6, but not a negative 3, or not a negative number, because a negative number would be a reciprocal, which will bring the x back in the numerator. We're saying the x in the denominator. Then the limit will equal 0. If you have an x in the denominator with a positive exponent and no x's in the numerator, then the limit is 0. and so on here. If we let x go to negative infinity, if x is less than 0, then this is also equal to 0. All right, here's a quick example of this. If we let x go to infinity for this expression here, this theorem says that we're actually talking about this part. Remember that a limit of a constant, or actually two separate monomials, you can break them up into two separate limits. And the limit as x goes to infinity for 5, it's just 5, because there's no place to put the infinity. There's no x here. So the 5 doesn't change, it's constant. But if you let x go to infinity, if x gets really, really big and you square it in the denominator, then that's going to get smaller and smaller as we let x get bigger and bigger. That's a concept that you're going to have to wrap your brain around. Like if I put in a 4 here, 4 squared would be 16. 2 over 16 is quite a small number. But if I put 1,000 down here, 1,000 squared is 1,000,000. So 2 over 1,000,000 is even a smaller number, a very, very small number, and so on. Then if you let x go to infinity, that's going to shrink this down to a very small number, and we can say that that's 0. So you have 5 minus 0 is 5. Let's explore that fact a little bit more, or concept. Consider the ratio of r is equal to a over b. If we let a get really big, then the ratio of a over b is going to get really big. Really big meaning like infinity or 1,000,000 or however big number you want to say. If we let b get really big, then we're dividing by a really big number, so that r will become very, very small. Okay? So let's find the limit of this expression here, this rational expression. In the book, they tell you that, you look at the top and the bottom, and you get, as x goes to infinity, this is going to get increasingly larger, and you're going to subtract 1 from it. It's still going to be a very large number, like infinity. The denominator also is going to keep getting larger, and that's infinity. If you have infinity over infinity or 0 over 0, that's called indeterminate form. You really don't know what that is. We can't say, we don't know how to divide infinity by infinity. So we'll have to use some work here. If we let x go to infinity, this part doesn't matter, so we can say that that's 0. But then if we have that 0, then these x's kind of cancel out. So now we have 2 over 1, which is 2. So this limit, as x goes to infinity, is going to be 2, because all of this is going to go away, and this becomes 1 when we reduce the x over x. And from the graph, you can see as we let x go to infinity, the y value, or f of x, is trying to get to 2. And if we let x go to negative infinity, although it doesn't ask for that, then the y value is still trying to get to 2. Remember, another way to think about a limit is, as x is trying to get to infinity, what is this trying to get to, right? As x goes to infinity, what is this value trying to get to? Well, it's trying to get to 2. It'll never get there, but it's trying to get to 2, and that's what this value is. Okay, we have 3 examples here, and let's see. Let's start with this one. Okay, if we let x go to infinity, this doesn't really matter here. Okay, so we're looking at this, and we can see that these two, infinity squared over infinity squared, we can just eliminate that. So this limit should equal 2/3. If we look at it on a graph, we can see that it does go to 2/3. Let's look at this one. If these are infinity, then adding 1 and adding 5 is not going to matter. So, but if we eliminate one of the x's, then we're going to get 2 over 3 times infinity. Or if we let x become infinity, that means we're going to have 2 over a really big number, right? So this is actually going to get smaller and smaller. And we can say that limit is trying to get to 0. On this one, if we eliminate that, this will make an x here. So if we let x go to infinity, then this whole thing goes to infinity. And what happens when the limit goes to infinity? The limit does not exist. Okay? All right. So this is it written out as a rule. So if you like notes like this, then you can copy this down. It just says if the degree in the denominator is less than the degree in the numerator, then the limit of the rational function is 0. And in pre-algebra, I told you that if the exponent on the denominator is larger than the exponent in the numerator, that's bigger on the bottom, Bobo. So that means y is equal to 0. Okay, so the function is going to go towards 0. That's where your horizontal asymptote is. Right? Now, if the degree of the numerator and the denominator are equal, like if this was a 4 also, then these cancel, and that will depend on the number in the front. If this was a 2 and this was a 7, then the limit would have been 2/7 because these cancel if the degree in the numerator and the denominator were equal. Now, if it's the other way, if it's like x to the 4th over x squared, then you're going to be able to eliminate that and make that x squared. And if we let this go to infinity, then this whole thing goes to infinity and it does not exist. Okay, or there are no horizontal asymptotes. Okay, that's what all this means here. All right. This is just a good graphic of what bigger on the bottom looks like. If it's bigger on the bottom, right, then the graph is going to start to, or try to get to 0. Okay, and then here's my horizontal asymptote, y is equal to 0, which is the x-axis. All right, here's a tricky one. We have the square root thing going on here. These are both the same function, or the same expression, but this one's trying to get to positive infinity, this is trying to get to negative infinity. There's a concept here that's kind of tricky, is that if we take the square root of x squared, here's the square root of x squared, if we square the x and take the square root, as long as x is going to positive infinity, we want positive values of x. For positive values of x, like 4, 7, 200, right? For 4 squared is 16, take the square root, that's going to give me x. But if we're going to negative infinity, we use negative values of x. Let's say negative 4, then negative 4 squared is positive 16. We take the square root of positive 16 and we get 4 again, so that means we lost our negative sign. So when we're going to, if we let x be negative, then we have to put a negative on this function here. Otherwise we lose that negative sign when we square it and take the square root. So that's the only tricky part about this. Okay, so if we let x be positive, then you have to understand that taking the square root of the square is going to be a positive x. And if we take the square root of a square on this, we lose that negative sign, so we have to add another negative to make sure that we understand that x is negative. So this part doesn't matter. So what happens here? This becomes x, right? The square root, and then we have the square root of 2. Right, this part becomes x, so they cancel. So you see what's going on here, and the same thing over here. This is going to cancel, but we have to put a negative on there because we lost that negative if x is negative. So here we go. If we let x go to positive infinity, then our horizontal asymptote is equal to y is equal to 3 over square root of x, or that's what our horizontal asymptote is. And if we go the other way, we're going to have to put a negative on it because the graph is going to go to negative 3 over rad 2 in this direction. Let's talk about some trig functions here. The sine curve looks like this, right? It goes like this in both directions. So if we let x go to infinity, well, we don't know because it's going to keep going up and down. It can't make up its mind. So we say that limit does not exist. We call that oscillating. Okay? And if we have this function, we divide it by x, we're actually going to have something called a dampening effect. And the work for that is all here. But if you look at the graph, it's a dampening effect, meaning that it's going to get lower each time. So as it goes to infinity, we can see that it actually goes to 0. Okay, it's trying to get to 0 if we let x get larger and larger to infinity. All right, now find infinite limits. Now before we just talked about where x is going to infinity. The function approached some kind of number, but now we have infinite limits. If we think about this, if we let x go to infinity, what's going to happen to this? Well, the limit goes to infinity. Okay. Okay, before we said the limit doesn't exist, but this goes infinity, which means that the limit just goes to infinity. And so on this side, it also goes to negative infinity. So as x increases without bound, the cube of x increases without bound. So we write that the limit of x going to infinity for x cubed is equal to infinity. So as we let x go to infinity, then the y value goes to infinity. And if we let x go to negative infinity, the y value goes to negative infinity. Let's finish this off here. You notice that here, if we let these cancel, these two are the same expression, except this is going to positive infinity, that's going to negative infinity. These cancel, so we're going to have 2x. If we let x go to infinity, then this is also going to go to infinity. Okay, so this goes to infinity, which means that there is no horizontal asymptote. And when we're talking about finite limits, we're talking about a horizontal asymptote, and this has no horizontal asymptote because it goes to infinity. And going in the negative x direction, negative infinity, same thing. We're going to end up with 2x again, and this is going to be negative infinity. So y is going to go to 2 times negative infinity, which is also negative infinity. There's no horizontal asymptote there either. Remember, it's bigger on top. There's no horizontal asymptote, but the limit goes to negative infinity. All right, here's some long explanation of why that works. So if you want to figure that out, you can. Okay, so I'm going to talk about this one. There are a lot of places in your textbook that show you why you shouldn't depend on your calculator. This is one of the good ones. If you are the kind of people that just grab your calculator, put that in, and just look at the graph, this is one of the places where it's going to kind of screw you up. Okay, if we look at this function on our graphing calculator, okay, I've gone ahead and inputted the function into my graphing calculator, and then I'm going to go ahead and graph it. You can see that even if I zoom in, it looks like there's a horizontal asymptote at 1, or the limit at infinity approaches 1 on both sides. And even if you zoom in more, that even more looks like that. You can zoom out, zoom out, zoom out, right? Looks like it goes to 1. Kind of. Now, do you trust your calculator, or are you going to check the actual work? Now, if I change my window, let's go to, on the x-axis, I'm going to go to -1,000. And then I'm going to go to +1,000. So I'm going to widen my window. I don't care about the x, y value right now because, well, let me change that too. Let me make that to maybe to like -4 and +4. Okay, now if I look at the graph, guess what? This graph goes all the way up this way and down like that. So you didn't see that. All we saw was this little part right there, that little valley, and it looked like there was a horizontal asymptote. But actually, it was starting to creep up. Or by the time we get to 1,000, we actually see that the horizontal asymptote is at 2, not 1. So this is very tricky. This is the same function. I just widened my window. So be very careful about trusting your calculator. Okay. Now you remember how I zoomed in and zoomed out? It even looked fine. Okay, let's go to my window again, and let's go to standard window. Same graph, but look how it looks when I have a -10 and 10. Even if I zoom out, okay. Now this is even at 100. Okay, I'm both. Oh no, not 100. That's 37. So like at 40 and 40, it still looks flat. Even at 75 and 75. Still looks flat. So you got to be real careful. You think you're looking at the graph, but now you see at about 150, -150, you see it starts going down. And if you keep zooming, see now you're starting to see some things going on with the graph. So you got to be real careful. Okay, that's it.